It's your friendly math tutor, Miss C here, and we are talking about sine functions once again. Specifically, we're talking about phase shifts today and how phase shifts not only impact the graph of y equals sine of x, but also impact our solutions when solving sine equations. So let's do a quick review of our sine wave. So sine has critical values every 90 degrees. Remember, this graph is infinite, right? So it goes on in both directions forever. So for our purposes, we're going to start at 0, 0 and move to 360 degrees just because those are nice numbers. So what you're going to notice is we start at 0, we pop up to 90 degrees right here. And that is our maximum of 1. We pop back down 90 degrees later to 0, and then down to our minimum right here of -1 at 270 degrees. And finally, we go back to 0, and that is our full sine wave cycle. And that pattern of critical values repeats every 90 degrees. Now, when we have a phase shift, what that means is that our graph is shifted or moved horizontally to the left or to the right by a specific number of degrees. Just as a reminder, trigonometry operates on 2 different forms of measurement. We're in degree mode, but there's also another mode called radians or rads, to be covered in another video. But graphs with a radian measurements can also have phase shifts. So here's how a phase shift looks. So on this graph, you're going to see my red circles from where our critical values were before. So let me just get rid of those. Okay, so on a phase shift, what we're going to notice is normally we would start at 0, 0, but we're starting at 30 degrees here. What that means is that our graph has shifted to the right 30 degrees, and that's true for every single point. So our first 0 value that we see when we're in the domain of 0 to 360 degrees is at 30 degrees. Our maximum then happens at 120 degrees. And then we hit 0 again at 210 degrees, pop down to our minimum at 300 degrees, and then we finish our sine wave at 390 degrees. So what's interesting about this is our full sine wave starts at 30 degrees and ends at 390 degrees. That's a 30-degree shift for a complete cycle. So you might be thinking, like, what does this equation even look like? And it looks like this. So if you remember from when you studied quadratics, anything that was like x minus something within the parentheses that were squared shifted your graph. This is the same idea. This x minus 30 shifts the graph right. So you're interested in how to make this part of your equation 0. So whatever x takes on to make that 0 tells you the phase shift. In this case, x would have to be 30. 30 is a positive number, and in math, positive moves our graph right. So that's how this graph gets shifted 30 degrees. How do I describe the transformation every single time? So we're going to practice that next. In this case, we have y equals the sine of the quantity x plus 120. Remember, we're interested in how we make this part 0. So what value does x have to take on? X would have to be negative 120 degrees. Negative in math moves our graph left. So the graph of this particular sine wave is shifted left 120 degrees. In this case, we have the y equals sine of the quantity x minus 45 degrees. What does x have to be to make this entire chunk of our equation 0? If you said positive 45 degrees, you are right. Positive numbers move our graphs right. So our sine wave has been shifted to the right 45 degrees. And finally, we have y equals sine of the quantity x plus 270. We're looking at what x needs to be to make this part of our equation 0. If you said it's negative 270, you are right. Negative moves our graph left. So our entire sine wave is shifted 270 degrees to the left. All right, so how do phase shifts affect your solutions or your answers when you're solving an equation? Really simply put, because the phase shift shifts the value. So for example, you can see I've highlighted our blue graph, and you're going to see that my zero value starts at 30 and then a full cycle completes at 390 degrees. You might end up with values that are outside of the domain that would typically have been inside of the domain. So that means you might have fewer answers within a given domain and maybe more answers. The difference is it's not going to be as predictable as it has been when we were just solving for like sine of x equals 0.2 or like 4 sine of x equals negative 0.9, right? You're not going to have answers exactly in that 0 to 180 degree arc like you did for all positive values before, and the same goes for the negative part. So we're going to explore that next as we solve 4 different sine equations. All right, our first problem is in the domain of 0 to 360 degrees. We have sine of the quantity theta minus 120 equals negative 0.75. I always think it's a great idea to get in the practice of identifying our transformation or how the graph has been transformed, in this case due to a phase shift, because we won't always have a graph like the one I've put on our page in front of us. And it's good to be able to know what's happening so you can visualize whether or not your answers are accurate. So let's go ahead and identify the phase shift. Remember, I've highlighted the part in yellow that tells us what our transformation is like. We're interested in making that part within the parentheses 0. So what value does theta have to take on for that to happen? It's 120 degrees. Okay, maybe I should grab a pen. It's 120 degrees. 120 degrees is a positive number. That means it moves our graph to the right that amount. So our whole graph shifts 120 degrees to the right because theta is a positive number. That's how we move to the right. Okay, what that means is every single value on my graph moves 120 degrees. So I just am going to show you on this graph. We normally start at 0. We're starting at 120 degrees. And then we start our cycle of 90-degree changes. So we go from 120 to 210. That's our maximum, right? But if we are looking from peak to peak, we're going to see that there's a shift of 120 degrees between our original sine wave, which is the red graph, and our transformed sine wave, which is the blue graph. All right. Now that we know what the transformed graph looks like, I'm going to go ahead and draw in y equals negative 0.75 so that we can see where our solutions are going to lie. And this is a very rough line that is not straight at all. So that's a unique problem. Okay, remember we are looking, I'm going to put our domain in as well. We're going from 0 to 360 degrees. So we're looking at where that line, that rainbow line that I drew in, intersects with our blue graph. We can see that there is an intersection point right here. And I should say between the 2 yellow bars that I drew, which represent our domain. I'm following our graph, and the next point that I see an intersection is right there. So I know I'm going to have 2 solutions, but they're going to be pretty different than what I've seen in the past. They're pretty far apart. Okay, they are still within that 180-degree realm, but because my graph has been transformed, pretty far apart. They look much different than they have in the past. Okay. So let's go ahead and solve. So we're going to solve using the same first step that we've done before. We're going to start by taking the inverse sine of both sides, and I'm going to write this out so you can see exactly what happens because we've never had values other than our variable in the parenthesis. And I'm going to show you what happens when that is the case. So all right. So when we take, I forgot to write sine there. When we take the arc sine of values, the arc sine makes the sine go away and we're left with theta minus 120 equals I'm going to put the arc sine or the inverse sine of 0.75 in my calculator. Remember that you need to be in degree mode. And when I do that, I get negative 48.59. Okay, before we manipulate this equation more, I am going to come over here and I'm going to use my property to find the value within the 180 degrees like we've done in the past. It's really important that you do this at this point. If you don't, you're going to end up with the wrong answer. So I have theta minus 120 degrees equals 180 minus negative 48.59. So I like to set that up here because if you do this out of order, oh my, I can't get that 9 written. Okay, if you do this out of order, you won't get the right answer. Okay, so I'm going to come back to my pink equation and work that, and then we will move to our blue equation. My next step is to add 120 degrees to both sides. When I do that, I get theta equals 71.41 degrees. That is a solution within our domain, okay? And now I need to see if there are any other solutions if I apply the period property, which basically says that if I add or subtract 360 degrees from this value, I'm going to get another value that's true. But when I do that, 71 plus 360 degrees or minus 360 degrees does not give us a value within our domain. So this is one of our solutions. And now let's go over and work the blue side. So I have theta minus 120 equals 180. I've got two negatives, which makes this positive. That gives me 228.59 degrees. But we are not done yet because that's not a solution because we don't have theta by itself. So we're going to add 120 degrees to both sides. When I do that, I get theta equals 348.59 degrees. That is within our domain of 0 to 360 degrees. So that too is a solution. Now, I should double check that if I add or subtract 360 degrees to this value, that I am not within our domain of 0 to 360, and I am not. So these are our two solutions that we saw on the graph. To double check these are correct, I highly recommend that you pop these into the equation and make sure that you get approximately negative 0.75 out every single time. It is just a way to check that you didn't make a simple mistake. Let's move on to our next problem. All right, our second problem is up. We're going to start by identifying our transformation. I think that's always a great way to start so you can have that idea in your head of what this graph looks like. So the phase shift is negative 25 degrees. Remember, we're interested in what makes what's in the parentheses 0. Specifically, what value does theta have to take on? A negative number in math moves our graph left 25 degrees. All right. So if your teacher asked you what the transformation was, you'd say the graph shifts left 25 degrees. All right. Let's go ahead and solve this, keeping in mind as we look at our sine waves, the red graph is sine of theta and the blue graph is our transformed graph. Below, we're looking for values that are positive exactly 1/6. So if I were going to draw the line for possible solutions, it's going to be really close to 0. But what we're going to see is we're looking for the intersection with the blue graph. We've got one right here very close to 150 degrees. I'm following my blue graph, and I've got another one right here pretty close to 335 degrees. So that's approximately where our answers are going to reside. So let's go ahead and find these solutions within 0 to 360 degrees. So I'm going to start the same way that I always do. I'm going to take the arc sine or the inverse sine of all of this, and I'm writing this out one more time so it's really clear what I'm doing and what happens. So when you take the arc sine of any value in the parentheses, the arc sine gets rid of the sign but leaves what's in the parentheses. So I end up with theta plus 25 equals the arc sine or the inverse sine of 1/6. And when I put that into my calculator in degree mode, it's a good chance to check that, I get 9.59. At this point, I am going to set up my property that looks like this. Theta is equal to, not equal to, theta plus 25 degrees is equal to 180 degrees less 9.59 degrees. You're going to notice I'm saying degrees, but I'm not writing degrees because sometimes those little degree marks end up looking like zeros, and then that's just bad news. All right, so we are going to solve the left side. So I'm moving the 25 degrees over. When I do that, I get theta equals negative 15.41 degrees. While this is a solution, it is not a solution within our graph because it's not between 0 and 360 degrees. I know this value repeats again every 360 degrees. I know that if I subtracted 360, it's going to be too small because this is already outside. But if I add 360, I'm going to get a value within our domain. So when I do that, I get 344.59 degrees, and that is one of our solutions. And that actually, if we look back at our graph, is really close to the 335 that we estimated based on my very crooked line that's supposed to represent y equals 1/6. All right, we're going to do the same thing to our other equation. We are going to simplify this. So we end up with theta plus 25 equals 170.41. And then we're going to deduct 25 from this because I'm trying to get theta by itself. When we do that, we get 145.41 degrees. Okay. And I could add or subtract 360 to this as well, but that is going to push us outside of our domain. Those values exist on this wave. They just don't meet the criteria that we have on this graph. So let's pop back up and make sure this looks pretty close to where we thought. We thought it was going to be really close to 150 degrees based on our graph, and it is in fact very close to 150 degrees. So as always, you should pop both of these solutions into this equation right here, and you should get out approximately 1/6. And I say approximately because this is a rounded value that we wrote, so it's not going to be exact. All right, moving. All right, we have our next problem. We're going to start by identifying our transformation again. I'm looking again, just as a reminder of what theta has to take on to make this 0, and it is 100 degrees. 100 is positive. That means our graph moves to the right 100 degrees. You can see that I've illustrated that above. So we know that this is a different domain. We are looking from negative 360 to positive 360, and I'm going to attempt to draw a very long line. So we are seeing how that goes. It's going to be about here. And as always, our red graph is the graph of our untransformed sine wave, and the blue graph is our transformed sine wave. So let's see, where does this rainbow line intersect with our blue graph between negative 360 degrees and positive 360 degrees? I see a point right here. I see another point right here. I see a point right here. And I see another point right here. So we are going to end up with 4 values. All right, let's get started solving this. So I'm going to take the inverse sine of both sides. I'm not going to write that I'm taking the inverse sine of both sides. I'm just going to do it on this side. Maybe if I grab a pen. Okay, theta minus 100. And then I'm just going to say I'm taking the arc sine of 0.45. When I do that, I end up with theta minus 100 equals the inverse sine of 0.45. Again, just a reminder. Your calculator should be in degree mode. The most common error I saw was the wrong mode. Okay, remember at this point, we go ahead and we come over here and we do our 180 degree property. So we say theta minus 100 equals 180 minus 26.74. Again, you have to do it at this point. Otherwise, you are going to get the wrong answer. All right, we are now going to go ahead and solve. We're going to add 100 to both sides here because we're trying to isolate theta. When we do that, we get 126.74 degrees. That answer falls within our domain of negative 360 to 360 degrees. That is one of our answers. Now, we are going to apply our property by either adding or subtracting 360. If I add it, I'm going to be over my domain, so I'm going to subtract it. So I'm going to subtract 360 from this, and I'm going to get my next value. So 126.74 less 360 gives me negative 214.59 degrees. And that is an answer within our domain. So these are both solutions. We're going to move over to the right now. We have theta minus 100. And then we're just going to do this math. 180 minus 26.74 gives us 153.26 degrees. This is not our answer because theta is not by itself. So we need to add 100 to both sides. When we do that, we get theta equals 253.26 degrees. That is a solution that falls within our domain. Again, this is the time where we're going to say, okay, can I add or subtract 360 degrees to find another value on this wave? As a reminder, sine waves repeat every 360 degrees in both directions, which is why we say plus or minus. If I add 360, I'm going to be way outside of my domain. But if I subtract 360, I'm going to be within my domain. So when I say 253 degrees minus 360 degrees, I get theta equals negative 106.26 degrees. And that solution falls within our domain. These are all four of our solutions that we identified. Once again, please, please, please put these into the equation and solve it, and you should get approximately 0.45 as your solution. This is the best way to make sure that you have accurately solved, and it gives you a heads up, especially on a test, if you're mixing up steps so you don't do it on every question on your test. One more problem coming up next. All right, we are to our final problem, and we are going to start the way that we always start by identifying our transformation. In this case, phase shift once again. Theta has to take on the value of negative 180 degrees to make what's inside the parentheses 0. Negative numbers moves our graph left 180 degrees, and this looks like a pretty perfect double helix. So our domain is different. Again, we are only looking for solutions from negative 360 degrees to positive 360 degrees. So let's go ahead and get started by taking the inverse sine of both sides. When I do that, I end up with theta plus 180 equals the arc sine of negative 1/8. And I guess I should have drawn a line here. Negative 1/8, as a reminder, what scale am I on? 1, 2. It's going to be like here in this area. Okay, maybe I should have used a pen instead of a highlighter because that's a really thick line. We're looking again at the blue graph. That's our transformed graph, whereas our red graph is our regular sine wave. So I see that I have two solutions. I've got one here and one about there. So we're looking for two solutions. All right. And that yellow line represents y equals negative 1/8, in case you're wondering where I got that from. Okay, so we are going to say theta plus 180 degrees, popping the inverse sine of negative 1/8 into our calculator, and we end up getting negative 7.18. Okay, at this point, we come over here and we set up our 180 degree property. So 180 degrees minus negative 7.18. Be careful here. The first time I solved this, I accidentally dropped my negative. And obviously, when you drop a negative in math, that's bad news. So just make sure, take care not to do that. Okay, I'm coming back to the blue side, and I'm going to go ahead and solve. I'm going to subtract 180 degrees from both sides because I am getting theta by itself. When I do that, I end up with negative 187.18 degrees. That falls within our domain of negative 360 to 0 degrees. Okay, I still want to just always get in the habit of doing this check. Are there any other values within our sine wave? Remember, it repeats every 360 degrees. So I'm going to say if I add or subtract 360 degrees, do I get another value that falls within our domain? The answer is no. They're both either too big or too small. All right, coming over to our pink side, we still have theta plus 180 degrees on this side. And then we have 180 minus negative 7.18. When we do that, we get 187.18. You might be thinking, well, I've got positive 180 degrees on both sides. Why didn't you just like cross out the 180s? I would totally do that if I weren't making a video. You can also totally do that, or you can do it the long way with me to make sure that we aren't being confusing. So when we do that, we end up with 7.18. All right, so this is a solution. Unfortunately, it's not in our domain. So if we look at our graph, it's going to be about right here. Probably up a little higher, but that's outside of our domain because it's bigger than 0. So we are going to apply our property. So we are going to think about, can we find a solution within our domain if we add or subtract 360 degrees? Well, if we add 360 degrees, we're already outside of our domain with positive 7.18. So we can't do that, but we can certainly subtract 360 degrees. And when we do that, we get theta equals negative 352.82 degrees. If we look at our graph, we see the value, negative 352.82 degrees. Boy, I didn't put a decimal point there. Looks like a much different number. Where that pink arrow lies or points to. All right, this is how you solve sine equations when you have a phase shift present. Remember, the order matters. Make sure to subscribe for more math videos. This is one of many videos I'm coming out with on trigonometry, so you don't want to miss those. Till next time, y'all, you've got this.